Hello guys, in this video, I'm going to start a new unit to introduce a set of interesting functions called loop functions. Loop functions in R allow us to execute loop-like behaviors in a compact form. These functions typically have the word apply in them and are particularly convenient when we need to execute a loop on the command line or in R console when using R interactively. These functions are some of the most powerful functions in the R language. To motivate loop functions, let's say we are analyzing a data set stored in the form of an R data frame, and we want to compute, say, the mean of each column. We could do copy and pasting 3 times and retrieve these 3 columns individually. But what if the data frame has many columns? As we've already learned about loops, like for loops and while loops. Here we can write a for loop to iteratively compute column means for a very large data frame. However, loops are slow and not very expressive. A for loop conveys that it's iterating over something, but doesn't clearly convey a high-level goal. Besides, they are sort of loosely structured and are not very suited to be typed line by line when working interactively with the console. So you may wonder, is it possible to execute a loop in a very small amount of space, like on a single line? The idea we may want to apply is the lessons we learned from vectorized operations. A bunch of operations in R are vectorized, meaning that they can operate on whole objects directly and apply an element-wise operation between these objects without need to incurring explicit loops. We've seen how R's vectorization capabilities help in eliminating loops. Actually, R's vectorization capabilities are not restricted to operations expressed by these built-in operators. In R, there are a couple of loop functions pertaining to the base package, which allow us to apply an operation expressed by adding arbitrary function to a collection of objects. They make R's vectorization capabilities more general and powerful. Because these functions typically have the word apply in their names, they are usually referred to as the apply family of functions. Let's first take a look at the workhorse function in this family. That is the lapply function. And the idea behind lapply is that you have a list of objects, and you want to loop over the list of objects and apply a function to every element of that list, and finally combine the results into a new list. So it's a very general concept, and it can be used to do a lot of computations in just a little bit of typing. Basically, the lapply function has 3 parameters. The first parameter called x and expects a list object. If x is not a list object, then it will be coerced to a list object if possible. That's why the full name of the lapply function is listapply. The second parameter expects a function or the name of a function. There could be other arguments passed into this function at the point of call. All of them can be captured by this special parameter. With the lapply function, now we can implement our repeated mean computations with this single line of code. Here, the lapply function takes this data frame as the first argument, and the mean function as the second argument. When it runs, it applies the mean function to each column of this data frame as a data frame is a special list of its column vectors. And finally, the 3 column means are returned in a list structure. A remark I would like to give here is that when passing a function to another function, we do not need to include the parentheses as we do when calling a function. lapply applies a passed-in function to every element of a list, and every application of the passed-in function consumes one element in the list and uses that element as its own first argument. To help you see this point, let's consider an example using lapply together with this random number generator function. The random uniform function takes 3 arguments. The first specifies the number of random numbers to draw. The second and the third arguments specify the lower and upper bounds of the interval from which the random numbers should be drawn. All of these arguments should be a single value instead of a vector of values. Now suppose we are going to create 3 sets of random numbers of varying lengths all at once. Here we pass a vector of 3 numbers, which will be coerced to a list of 3 elements. It makes the random uniform function applied 3 times. And these 3 elements all get matched to the n parameter of this function in these 3 calls. So the first call uses 1 and generates a vector of length 1. The second call uses 2 and generates a vector of length 2. And the third call uses 3 and generates a vector of length 3. And functions that we pass to lapply may have other parameters. Like this random uniform function here, it has the min and max parameters as well. This is where this special parameter comes into play. Then the arguments targeted to the min or max parameter can follow the function argument. So this named argument will be passed down to the random uniform function and used every time it gets called. As you can see, this set of numbers definitely have a greater upper limit because we've set the max parameter to 10, which is larger than the default value 1. But what if the inputs we want to vary across different applications of the passed-in function are not supposed to be used by its first parameter, but something after that? So for example, what if we don't want to vary the length of this sequence of random numbers, but want to vary their upper limits? Then we can use an anonymous function to customize argument passing behaviors of the function being applied. Anonymous functions don't have names and can be quickly generated on the fly. Here, I'm writing a function which takes an element from lapply's first argument and uses it as argument to the max parameter in the inside call to the random uniform function. As a result, these 3 sequences are generated with different upper limits. The random number generation process for the first sequence seems to be deterministic because the upper limit coincides with the lower limit, so only one can be drawn. And the other 2 sequences have 2 and 3 as their upper limits respectively. And the ellipsis is used in this function definition because we want it to capture additional arguments for this inside function call. This example illustrates a way of using anonymous functions to customize argument matching for the function being applied. Instead of creating an anonymous function on the fly, you can also define a named function first and use its name in this lapply function call. Whether you use an anonymous function or you define a function first depends on the context. If you think that function is something you are going to need a lot in other parts of your code, you might want to define it separately. But you are just going to use it for a single call to lapply, then it's probably simpler to use an anonymous function. And it turns out we'll use anonymous functions a lot when using the apply family of functions. Because functions are first-class objects in R, lapply can also work with groups of related functions as with lists of data objects. Here I define a list that encapsulates 3 functions that implement 3 different mean calculations, and then call the lapply to apply these 3 functions to the same set of random numbers in batch. The anonymous function here takes a function from this list and applies this function to the vector x within its body. And the result gets flattened using the onList function, which we introduced along with lists. After knowing the use of lapply, next, I'm going to introduce several key variants of lapply in the apply family. Here is a summary of them. The first one is sapply, which is a variant that tries to simplify the result of lapply if possible. mapply is the multi-dimensional version of sapply, which applies a function over a set of arguments. Apply is used to evaluate a function over the margins of an array, and tapply allows us to apply a function over grouped elements. So let's first take a look at the sapply function, which generates vector outputs. Recall that lapply always returns a list, but sometimes you don't want a list. Sometimes you just want something simpler. Then you can use sapply, which tries to simplify lapply's results if possible. For example, if the result is a list whose every element is a length 1 vector, then what sapply will do is it will return a vector of these elements. If you take a closer look at the body of sapply, you can find essentially sapply calls lapply on its input, then applies these simplifying algorithms. So sapply simplifies things and can return a list, a vector, or a matrix, whichever suits most. This is a desired feature when we program interactively, but in a non-interactive settings, this makes it difficult for us to predict the exact form of results. So sapply should be avoided in non-interactive settings. Next, I'm going to introduce another member in the apply family, mapply. mapply is a multivariate version of lapply and sapply functions. It allows us to apply a function in parallel over a set of different arguments. One thing you may have noticed about the lapply and sapply functions is that they only apply function over the elements of a single list. So what happens if we have two lists and we want to apply a function over them? For example, suppose we want to use the random normal function to generate different sequences of random numbers by varying both length and mean. Can we pass two lists to lapply and use the elements of the first list to match the n parameter, while use the elements of the second list to match the mean parameter? Can we even vary inputs to all three parameters simultaneously? Unfortunately, lapply cannot be used for this purpose, but we can do that with mapply. Now suppose we have two lists. mapply can take multiple list arguments and then apply a function with the elements of the multiple lists in parallel. You may notice that the order of function arguments to mapply is a little bit different. It is because mapply can take an arbitrary number of list arguments. Here, the first argument to mapply is a function that we want to apply. And this ellipsis captures a sequence of lists. These lists each contain a different type of arguments we want to pass down to that function for its different applications. Here I give two examples to illustrate the use of the mapply function. Again, in this example, vectors will be coerced into lists first, and the first list is used for parameter m, while the second is used for the parameter mean. And the SD parameter will use its default value. So when the random normal function is first applied, it uses 1 for n and 1 for mean. When it is applied at the second time, it uses 2 for n and 2 for mean, and so on. In the second example, apart from the arguments for n and mean, I supply another argument which is targeted to the SD parameter. And as it usually does, R recycles this argument to make it match the length of the previous two arguments. That's why this set of random numbers have a larger variance. Because mapply can be used to apply a function with multiple sets of arguments, it provides much flexibility and enables us to vectorize virtually every function that doesn't allow for vector arguments. But some caution should be made when using mapply to vectorize a function. Let's consider an example that highlights a common mistake that people make. In many statistical applications, we may want to calculate the sum of squares for normalized data. Let's implement this calculation with an R function. Name it sum square. And then generate some data to investigate its effect. And it works. This call outputs the sum of squares with the data normalized by this pair of mu and sigma. Then, what if we want to make it generalize? Suppose we want to normalize the same data with 10 different choices of mu and sigma, and then calculate the sum of squares for 10 different sets of normalized data. If we simply replace these two single value arguments with these two vector arguments, which represent 10 mu's and 10 sigmas respectively, can we achieve our goal? What would happen? So as you can see here, it only returns a single value. Why? The reason is that this calculation is implemented via vectorized operations. So in this call, the two vector arguments were first recycled and then involved in this calculation in an element-by-element fashion. And the intermediate result are finally aggregated by sum to a single value. Since we just learned that mapply allows us to vary inputs to a function across its different applications, it seems to be a promising remedy. So how about changing the code to the following? We fail again. This code gives us 50 numbers, not 10 that we are expecting. The reason is that both mu and sigma were recycled to be the same size as x, and then used in 50 applications of this sum square function. So it is an element in x that messed up the number of times the sum square function have been applied. And we actually want to supply x as a constant input to each call to the sum square function. And this can be fixed by using the more argument parameter of mapply. This parameter is used to specify a list of arguments that need to be supplied as constant inputs to each call. Now, as you can see, the problem is solved. And we end up with 10 sums of squares. But if you think the syntax here is a little clunky, you can use a wrapper function named vectorize when you want to create a vectorized version of the sum function. This vectorize function actually calls mapply to do the real work, but provides a more convenient interface for us to specify arguments that determine the number of calls. So here is an example that illustrates how to use this vectorize function to vectorize this sum square function. And here we need to specify the parameters used to determine the number of calls. And it outputs a function object. And this vectorized version of sum square function can be used in a very intuitive way, as you can see.